In our high school math, we have always been told that if you're given a matrix, say this A matrix, just make a characteristic equation out of it. And that will help you find what we call eigenvalues of that matrix A. And then, for each eigenvalue, just solve this equation to get eigenvectors, right? But we have never been taught what these eigenvalues and eigenvectors actually represent in the real world. We were simply told to somehow learn the steps to calculate them and then forget about it. This is the main reason many people hate maths, because they are taught how to calculate things, but never why they matter or what they truly mean. So are eigenvalues and eigenvectors just some fancy numbers and vectors that pop out of an equation? Or do they have a deeper, more intuitive meaning? And most importantly, can we actually visualize them? Well, in this video, we are going to see eigenvalues and eigenvectors in action so that they finally make sense. Assume we have a random 2 cross 2 matrix like this. Now assume we have a point, say 0, 1, which we can represent using this vector. Now if we multiply this matrix with this vector, we get another vector which is this point on the graph, and it is represented by this vector. So what we saw is this 2 cross 2 matrix acts as something which transforms a vector into some other vector. It is like stretching or shrinking a vector and then rotating it by some amount. This means if you take any point on this graph and apply this transformation, its new position is calculated by multiplying it with this matrix. So let me do something interesting here. Let me take all these points on this graph and apply transformation on all of them at once using this matrix. This is what the transformation will look like. The yellow dots are all the new output vectors. Let us first observe all the points along some line, say x-axis. You can see that the points along this line are rotated by some angle, and also it got a bit stretched, right? Now let us observe all the points along this line, or y-axis, where you can see that the points along this line are also rotated by some angle, and they also got a bit stretched, right? Now here comes the magic. This time, just observe all of the points along this line. The vectors along this line do not rotate at all. They only get longer or shorter. Such lines where the vectors do not rotate but only get scaled at some point are called eigenvectors. So, these two lines are the eigenvectors of this matrix. That was mind-blowing. Now for this matrix, one of the eigenvectors points diagonally at an angle of 45 degrees, meaning it lies along the line where x is equal to y. This direction stays the same, but the vectors along this line get stretched by a factor of 3. This scaling factor is one of the eigenvalues of this matrix. That means the eigenvalue corresponding to this eigenvector is 3. We also have this other line where x is equal to negative y. The vectors along this line neither gets rotated nor it gets scaled. It remains the same, meaning the eigenvalue here is 1. That's what eigenvalues and eigenvectors mean in real life. But sometimes it can happen that no real number satisfies the eigenvalue equation. What does that mean? Imagine this matrix and let us transform all of these points. If you observe clearly, this matrix rotates every vector by 90 degrees counterclockwise. Nothing is stretching or shrinking along any fixed direction. If we try to find eigenvalues, we end up with an equation that says x times x plus 1 is equal to 0. But there is no real number that satisfies this equation. This means that there are no real eigenvalues, and that tells us something interesting. There is no real direction that remains fixed under this transformation. Instead of stretching or compressing vectors along a particular line, the transformation rotates everything. This is a huge difference compared to what we saw earlier. Let's look at a real-world application of them. One surprising place where they show up is the page ranking algorithm of Google. at least the way it used to work in the 90s. Assume we have 5 websites numbered 1, 2, 3, 4, and 5. Now you can see these rays between different websites, like this ray between 1 and 2 denotes there is a link on website 1, which leads us to website number 2. Similarly, you can see a ray between website 2 and 3, which denotes there is a link on website 2, which leads us to website number 3, and this is how this structure is defined. Now, the most important question here is which website will have more traffic? Isn't this an interesting problem? You might be thinking how eigenvalues and eigenvectors might be playing any role here. You know that for eigenvectors, we need a matrix, and this is how we will construct this matrix. Here we have 5 websites, which means we will be having a matrix of size 5 cross 5, which has 5 rows and 5 columns. The value at position I and j in the matrix represents the probability of a user navigating from website I to website j. This matrix is called the Google matrix or link matrix, and it captures how web traffic flows through links between websites. Now, let's break it down. If you look at the first column, there are 3 outgoing links in website 1, which goes to website 2, 3, and 4, and thus all of them have a value of 1 over 3, which means there is a 1/3 chance of the user navigating from website 1 to website 2 or 3 or 4. Since we do not have any link from 1 to itself, that is why it has a 0 value. Also, there is no outgoing link between website 1 and website 5, and thus this value is also 0. Similarly, look at column 2. This will be 0 because there is no link from 2 to itself, and for the rest of them, we have one outgoing link from website 2 to every other website, which means a total of 4 outgoing links. Hence, we have a value of 1 over 4. This pattern continues for all websites. Now we will compute the eigenvalues and eigenvectors of this matrix. We find this nice solution. The most important thing to note here is that the largest eigenvalue, which is this one, gives us the dominant eigenvector, which is this. This eigenvector tells us the relative importance of each website in the network. The website with the highest value in this eigenvector will be the most important website, meaning it will get the most traffic. The largest value in this eigenvector is one which is of website 5, and thus it will be ranked 1 by the Google. Now this is the second highest number, which is for website 3, and thus website 3 will be ranked 2nd by Google. This way, we get the following ranking of all the websites. This is exactly how Google's PageRank algorithm revolutionized web search in its early days. This is just one of the many places eigenvalues show up. That was simply amazing. Now, if this video gets 8,000 likes, then I will make another video where I will show more applications of eigenvectors and eigenvalues. So good!